I'd like to talk to you about number 17 now. So number 17, we have a pretty simple base function. I encourage you to pause the video and just work out a table of values for -2 through +2 for x on this one, and see that you can get that base function graphed. Remember to focus first on x is 0 and x is 1, and you'll have a pretty good beginning of your graph. You'll have a y-intercept, and you'll know whether it swoops up or swoops down, whether it's a growth function swooping up or a decay function swooping down. So pause the video and then come back. Okay, assuming you're back, we'll start. I'll just go ahead and put the beginnings of those points in, -1 and an x value of 0 and an x value of 1 and an x value of 2, and that should get us in pretty good shape for graphing our function. We'll start with 0. So 4 to the 0 is, of course, 1, because anything other than 0 to the first power, or to the 0 power, anything other than 0 to the 0 power is 1, because I'm not using 4 as a factor at all. But there's still that ninja 1 hiding out in multiplication. 4 to the first is going to be 4. Okay, and 4 to the second power is 4 squared, so that's 16. Going the other direction, 4 to the negative first power is 1 over 4. So 1 over 4. And 4 to the negative second power is 1 over 4 squared, or 1 over 16. So we pretty quickly have a set of points that we can work with. Always remember that negative exponents do not turn the base negative. That is not their job. They turn the base into a divisor. They turn into the opposite of a factor, which is a divisor. Okay, so let's go ahead and plot those, and we can see that this is 4 to the x, and it goes right through them very nicely. All right, this one, the transformation of this function, the shifting of it, is a little different. I'm not adding or subtracting some of the x. Instead, I'm switching the sign of x. So that means that I'm going to have the same effect. I'm just going to copy these points over here. If we can predict what switching the sign of x is going to do here. So it's not going to make these points. However, it's pretty simple to change these points into something that you could plot on the graph if you think about what negative x is going to do. So see how you would change all of these points so you have them to plot, just based on the fact that we're just having the opposite sign for x. Pause the video and see what you can come up with. Okay, assuming you're back, what that means is if all we have to do is change the signs of all these x's. So if x is 2, that's like having an input here of -2, because I'm doing the negative of x. If I get the same effect as if I had for an x value of 2, as if I had an x value of -2. So I'm just going to change all my signs. I'm going to reverse all my signs. 0 stays the same. Okay, and that becomes the opposite sign. So now I've just reversed everything. So what you might predict is our function is going to be reflected over, it's going to be flopped over the y-axis. All the y values went to opposite x from the original function. So if I go over here and I plot this, notice I've got that. And this one is on the opposite side. 0 is still 0, 1 is still 0. These points have flopped over, and these points are flopped over. It's a mirror image across the y-axis. That's what I mean by a reflection. It is literally a mirror image. That's why we call it a reflection. So we'll plot this 4 to the negative x, and it works. Okay. Now, I'm going to deal with a slightly more complicated one now. which is going to be 2 to the x, but I've already got my basic points for 2 to the x, so hopefully you've already done number 15, so you have your basic points for number 18 for the base function of f to the x. So we'll plot those. I'm going to go ahead and go over here. I'm going to get rid of all of this that I had. And I'll plot those points, which we can confirm pretty quickly is 2 to the x. Okay. But what we have here is 2 to the 5 minus x. Okay. So I'm going to ask you to pause the video and see if you can figure out how we would come up with a set of values for 2 to the 5 minus x. Okay, assume you're back, and there may be a variety of ways you can do this, but here's what I recommend. What I recommend is copying over those points that you had over here, and then we're going to change our x values. Okay, we're going to have so what we need to do here is we need to take a look at what x values would get us the same exponent as we had here, because this 5 minus x is the exponent. We need to figure out what x has to be for 5 minus x to give us the same results. So for 5 minus x to give us the same result as 0, 5 minus x has to equal 0. So 5 minus 5 equals 0. So there we have it. That's 5 minus 5. So 5 minus 5 is 0. So that's 2 to the 0. And what would get us 1? 5 minus 4 would get us 1. And what would give us 2? 5 minus 3. Okay, you may be seeing a pattern at this point. Pause and see if you can figure out what these two would be then, because this needs to be -1 and this exponent needs to be -2. What would give us the same effect of -1 and -2? Okay, I'll go ahead and spill the beans. 5 minus 6 would give us -1. An exponent of -1 is 1/2. And 5 minus 7 will give us what we need here. So I'm going to copy that. And we get our function 2 to the 5 minus x. And there we have it. So our function is reflected. And it's interestingly reflected. It's reflected over a point that is halfway between 0 and 5. It's reflective across a line, I should say, at x equals 2.5. Okay. I'll let you ponder what that might mean and what that might imply about this this function situation. But as you can see, coming up with a simple table of values and then manipulating that table of values a little bit so that the x values have the same effect as they had in the base function makes it a lot easier. I'm going to pause this. I'm going to stop this one, and I'll do another video for the remaining ones.